So our final picture is going to look like this. Okay? Now there are numbers to put in here, and it's going to be a little hard putting them in to something of this size and making it legible to everybody, but you already know what the numbers are because you just figured them out and put them in there yourself. Just to be sure, our numbers are, let's make sure, we got 1.15 now, that's been corrected. We have 1.62, and we have 2.30, and we have 3.25. Of course, we have our 0.2, our 0.7, 1.2, and 1.7. Down here, we have our three slopes, which are, now, we have 0.940, but that was based on the 1.14. I'm just going to continue. Okay, this isn't really right. Okay. But I don't want to take the time to correct it. And 1.90. So we have our three slopes, and we've established that the ratio of this to this, the ratio of this to this, if we correct this, based on the 1.15 rather than 1.14, we get very nearly the same ratio, and any difference in the ratios we get is due to round off. Okay? Then we put our midpoint altitudes in here. We have what, 1.39 and 1.96 and 2.78. And I'm going to say the convention is we're going to label the length of any vertical line with an unadorned number, no rectangles, no parentheses, no circles, to the left of that line, okay? If we happen to label one to the right, we're going to put a little arrow there pointing to make sure that we see that we've violated the convention, but there's sometimes good reasons why we need to do that. Okay, well then we have the areas, and this one comes out 0.695. And this one, 1.96 times 0.5 is 0.98. And this one's going to be 1.39. Am I right? Okay? Mm-hmm. Now, these are the areas, these are the slopes. These are what we call graph altitudes. A midpoint graph altitude and the two graph altitudes for each figure here. These figures are all trapezoids, okay? We're not using a formula for the area of trapezoid, which is kind of ridiculous anyhow, because you can always decompose a trapezoid with a couple of cuts. Into a rectangle, you don't really need a formula, okay? But then you can derive the formula, and sometimes the formula is useful. Okay, well anyhow, then here we get, well these are accumulated areas. This one is 0.695. It's the area of the first trapezoid, moving from left to right, the direction we read in, okay? And it represents the total area from where we started to the end of that trapezoid, right? Now how did we get the total area here? That would be from where we started, which is here, up to here, right? Mm-hmm. So what would we do to get this number?
Add the two.
We would add this and this, right?
Mm-hmm.
So we add these and we get 1.675. Okay? And then what are we going to do to get this number? We could add all three of these numbers, right?
Mm-hmm.
Of course, here's the sum of the first two. We don't have to do that again. We just add this to this. Mm-hmm. So we just add the area to whatever we had up to the last one, and we get the area up to the end of this one. Okay? And that's going to be what? 2.9, that's going to be more than that. It's going to be 3.065. Yep. And since we're sticking to three significant figures, that's just going to now be 3.07. Okay? Do we understand how to label these things? Why would we do this? Well, it's because all these things can have a significant interpretation in terms of a temperature function or a flow rate function or whatever. And that's what we're going to talk about next. Okay?